Hello, and welcome to Cruising Through Calculus. My name is Alex, and today we're going to be looking at a variety of limit problems. I've compiled together a list of limit problems that you might see on a homework or a quiz or even tests, and I'm going to go through each problem and walk you through them step by step. I've even created a flow chart to help you guide yourself through these problems in case you ever get stuck at certain parts. Let's jump right in. For most problems that we go through, we're going to start with substitution, and this one is no exception. We're going to plug -1 in for x, and we're going to see what happens here. So we've got the square root of -1 plus 5. Well, of course, -1 is just +1, and then plus 5 gives us 6. Now, there's no way to simplify this, so we're already done. Let's look at the next one. Our first piecewise limit. These can sometimes trip students up, but there's actually an easy method that I've developed that you can use to help answer these questions. The idea is that you want to find the limit as x approaches your number from the left and from the right. But the trick is that you have to figure out which piece is which. So come on over here and draw a number line with me. In the very middle, go ahead and put the number you're approaching. Then label your two pieces. There could actually be more than two pieces. There could be 3 or 4. In this case, there are only 2. And we're going to do a quick graph of each. So for piece 1, 2x is graphed where x is less than or equal to 1. So less than or equal to 1 would be over here. That's piece 1. Piece 2 is where x is greater than 1, so it's going to be an open circle and greater than 1. Now remember, we need to find the left and right limits here. So as x approaches 1 from the left, well, let's see here. Here's 1. As we approach from the left, that's going to be equation 1. So here, we're going to find the limit of 2x as x approaches 1 from the left. We'll use substitution here, just 2 times 1, which is 2. That's our left limit. For the right limit, we come over here and notice that as we get closer to 1 from the right, it's the second equation we need to use. So we're going to approach 1 from the right of -x squared. Let's use substitution here. -1 squared is just going to be -1. All right, now we compare our two answers here. Notice that these are different numbers. That tells me what the final answer is. If you find a right limit and a left limit, and the two do not agree, your final answer is does not exist. By the way, if they had asked us to find the limit as x approaches 1 from the right, let's say, I would have come down here and used this answer. And if they had asked us as x approaches 1 from the left, I would have done this and just used this as my answer. By the way, notice the method that I used here. I drew a number line, put the number I was approaching down here, labeled my pieces, and then did a quick graph of each piece. This allowed me to easily figure out what the left and right limits are. I haven't seen this method in any textbook, and I haven't seen any teachers teach it. It's just a method I came up with. And if you use it too, this can help you. I see absolute values here. Let's start with substitution and see what happens. If I plug 1 in for x, I get -1 plus 1, which is 0, times 4, which is 0, and then -1 plus 1 is 0. So we do indeed get 0 over 0. Now there's something I'd like to do here, because this problem and slight variations of it show up so often that I've developed a method that you can use to quickly get the answer. Depending on what happens, you're going to get one of 3 answers. Either you're going to get does not exist, or 1, or -1. With slight changes to these last two here. I'll show you how to do each one. We're going to start by answering this question first. Then once we're done, we're actually going to find the limit as x approaches 1 from the right. And then finally, we'll find the limit as x approaches 1. So let's actually take a look here. The first thing that I'm going to do, although not entirely necessary, is I'm going to move this 4 to the front, like this. Then I'm going to come back here and I'm going to draw a number line, and in the middle I'm going to put the number that we're approaching, which is 1. Now we're approaching from the left here, so I'm going to pick a number that is to the left of 1, like 0. And what I'm going to do is substitute 0 in up here and then simplify. So we're going to get 4 times negative 0 plus 1 over negative 0 plus 1. Well, okay, negative 0 is just 0, plus 1 is 1. The absolute value of 1 is still 1. Down here, negative 0 is 0, plus 1 is 1. So what we get here is just 4 times 1, which is 4. So in this particular scenario, we got 1 for this part right here. Let's see what happens if we find the limit as x approaches 1 from the right. This time what we're going to do is we're going to pick a number to the right of 1, maybe like the number 2, and we're going to substitute it in for x here. So let's see here, we're plugging in 2 for x. Okay, so negative 2 plus 1 is negative 1. The absolute value of negative 1 is positive 1. And 1 divided by negative 1 is, of course, negative 1. So our final answer is 4 times negative 1, which is negative 4. So in this case, this absolute value part turned out to be negative 1. Let's look at the last case. The limit as x approaches just 1. Well, you might consider this the best case because you can automatically say the answer is does not exist. Now, this method that I've developed over here works as long as a couple of conditions are met, let's call them. First of all, you need to have an absolute value on one side and not on the other, and then the two pieces have to be identical other than the absolute value. You can have a number out here if you want. It's just that you're going to take your number and multiply it by either 1 or negative 1. Or in the case of D&E, it doesn't even change anything. All right, we actually did quite a bit more work here than we had to, because the question just asked us to find the limit as x approaches 1 from the left. But I still wanted to go through each scenario just so you could see what to do. A piecewise function. Since x is approaching negative 1 of a piecewise function, that means we need to find the limit as x approaches negative 1 from the left and the limit as x approaches negative 1 from the right. To do that, we're going to come over here and we're going to draw a number line. In the middle, we're going to put the number that we're approaching, which is negative 1. Then up here, we're going to label our pieces. There are only 2 pieces here, so just 1 and 2. The first piece is everywhere where x is not equal to negative 1. So we can't be equal to negative 1, but everywhere else is okay, like this. I'm even going to write a 1 here and a 1 over here. The second piece is only there when x is equal to 1, so that'll be just a filled in dot right there. That's our piece number 2. Okay, now to find the limit as x approaches negative 1 from the left, here's negative 1, we're approaching from the left. It looks like equation 1 is what we need to use here. So, let's find the limit as x approaches negative 1 from the left of x squared plus 2x minus 2. I'm just going to use substitution here and plug negative 1 in for x. Okay, what do we get here? Negative 1 squared is 1. 2 times negative 1 is negative 2. And then over here we have a negative 2. So that's going to be 1 minus 2, which is negative 1, and minus 2, which is negative 3. Okay, now to find the limit as x approaches negative 1 from the right, we come back over here, and as we approach from the right, it's the same equation actually. Now luckily I did all this work up here, so I already know what the answer is going to be. It's going to be negative 3. Now we compare our two answers. They're both the same answer. So that tells me that the limit as x approaches negative 1 of our function is negative 3. All right, let's see if we can find the answer to this limit. Substitution is always the thing you want to try first if you can. You can't really do it with piecewise functions because you don't know which piece you need to substitute your numbers into, so you need to do a little bit more investigation. But here, there's just this function right here. So let's just straight up plug negative 1 in and see what we get. I'm going to do this part in my head here. Okay, up top we have negative 1 plus 1. That's going to give me 0. And the fact that this negative here isn't going to change that that's 0. Here we're going to get negative 1 squared, so that's 1. Then 3 times negative 1 is negative 3, so that's 1 minus 3, which is negative 2, plus 2. So we get 0 over 0. This does not mean the answer is undefined. Instead, it means that you have more work to do. In this case, I'm looking here and I see the denominator and I'm thinking to myself that I can probably factor it. So let's take a look at that. What I need to do here is come up with two numbers that multiply to 2 and add to 3. And that should just be 2 and 1. This is perfect. Notice we have an x plus 1 up top and an x plus 1 down below. That means those will cancel. Let's see what's left over after we do that. Just the x plus 2 in the denominator is left. Now we can do substitution. So let's take negative 1 and plug it in for x. Okay, negative 1 plus 2 is 1. 1 divided by 1 is 1, and the negative in front means our final answer is negative 1. By the way, I chose this problem and future problems on purpose with this little negative sign in the front. You have to keep that negative with you the entire time, otherwise you might get 1 as your answer, which would be incorrect. Let's begin with substitution on this one. If I plug 0 in for x, I get 1 over 2 minus 1 over 2. So this is going to be 0 over 0. Remember, 0 over 0 means you have more work to do. It does not mean the answer is undefined. This is a complex fraction here. So what I'm going to try to do is I'm going to try to simplify it. The method I'm going to use is I'm going to look at the top piece and the bottom piece separately. And then I'm going to see if I can simplify them. The bottom piece is just x, so that's going to be pretty boring. But there is something that we can do with the top piece here. 1 over 2 plus x minus 1 over 2. What I'm going to do is get a common denominator. So I'm going to multiply this right side by 2 plus x over 2 plus x, and the left side by 2 over 2. Okay, let's see what happens when we do that. 2 times 1 is 2. In the denominator, we just get 2 plus x. Let's see here. We're going to get 2 plus x here because we're multiplying that by 1. Take a look. The denominators are the same now, so I can subtract the tops. Now, this is really important. I want you to focus very carefully on this because I cannot tell you how many students I've seen make this mistake. When you are subtracting the entire piece here. You're not just subtracting 2. You have to be sure to subtract the 2 and the x, like this. If you don't do that, you will get the wrong answer. All right, let's see here. 2 minus 2 is 0, so those will cancel. And we're left with just negative x on the top. Now, for this bottom piece here, x, I'm going to do really almost nothing. I'm just going to make it x over 1, and you'll see why I'm doing that in the next part. All right, I've taken my simplified versions and written them out over here. Those were actually kind of like scratch work. It's actually time to work with our limit now. So let's do this. Let's come back here to our limit, and let's replace the top piece and the bottom piece with those pieces that we found, like this. Now, when you're dividing with complex fractions, what you end up doing is multiplying by the reciprocal, and that's what we're going to do here. So we leave that top piece alone, and we're going to multiply by 1 over x, like this. This is perfect, because take a look. This x will cancel with that x right there. Let's see what we're left with. Notice it wasn't the negative that canceled, it was just the x, so the negative is still there for the ride. Now, we were approaching 0. Let's plug in 0. So in other words, we're using the substitution method right now. It looks like we're going to get negative 1/4. Okay. I noticed something right off the bat is that we have a square root here. But before I do any work with this, let's take a look and do substitution. If I plug 1 in for x, I get 1 plus 3, which is 4. The square root of 4 is 2, and 2 minus 2 is 0. And down here we get 1 minus 1. 0 over 0. That means we have more work ahead of us. Now, like I said, I noticed this square root right off the bat. We can't factor, this isn't a complex fraction, so what we're going to do is multiply by the conjugate. When you're multiplying by the conjugate, be sure to keep the first piece the same and the last piece the same. The only part that changes is this middle part right here. Another thing that you can also do, and I only recommend this if you're comfortable enough doing this, is when you multiply by the conjugate, the middle two pieces will always cancel out. So you only need to multiply the first piece by the first piece and the last piece by the last piece, which is what I'm going to do here. So the square root of x plus 3 times the square root of x plus 3 is just x plus 3. Negative 2 times 2 is negative 4. Another little tip that you can do is leave the other side unfoiled. I could go ahead and FOIL all this out, but as you'll see in just a second, if you leave it this way, that's better. All right, let's take a look here. 3 minus 4, that's just negative 1. Ah, take a look. This is why you want to leave the denominator unfoiled. The x minus 1 and the x minus 1 will cancel. Let's see what we're left with now that we've done that. Let's see here. We were approaching 1. We canceled things out. Why don't we substitute 1 in for x and see what we get? Okay, 1 plus 3 is 4. The square root of 4 is 2. And 2 plus 2 is 4. So our final answer is 1/4. Ah, I see trig. Let's start with substitution. If I plug 0 in for x, I'm going to get pi over 2 plus 0, which is pi over 2. The sine of pi over 2 is 1, so we get 1 minus 1, which is 0, all over 0. So we get 0 over 0. All right, that means we have more work ahead of us. When you're doing trig limits, there are 2 trig limits that you need to know. Think of these like facts. You can pull these out and use them at any time. Here they are. Most of the time, when you're working with trig functions, your goal is to get your limit problem to look like one or maybe even both of these. Now, looking at this, it doesn't really look like either of them at the moment, but why don't we focus on this sine of pi over 2 plus x just for a second. Now, there is a lot of trigonometry and a lot of trigonometric formulas. We're about to use one here. This is the sum formula for sine. It goes like this. The sine of the first piece, cosine of the second piece, plus the cosine of the first piece, times the sine of the second piece. Like that. Whew, getting pretty long. All right, now let's take a look and see, because this is going to simplify down pretty nicely here. For instance, cosine of pi over 2, that is 0. Sine of pi over 2 is 1. So we get 0 times sine, which is 0. Here we have 1 times cosine, which is just cosine. In other words, what we figured out is that the sine of pi over 2 plus x is actually just the same thing as cosine. So let's go back to our limit problem. Let's replace the sine of pi over 2 plus x with the cosine of x. Ah, look at this. This matches with this formula precisely, so that means the answer is 0. Ah, another trig problem. Let's substitute 0 in for x and see what we get. The tangent of 0 is 0. 2 times 0 is 0, so we get 0 over 0. That means we're going to need to use one of these two. Almost always in these problems, your goal is to take whatever the function is you're working with and use your trigonometry knowledge to make it look like one or maybe both of those. Let's take a look at this one here. I see a tangent up top, and I know that tangent is actually just sine over cosine. Now this is kind of like a complex fraction here. Why don't we take this 2x and write it as over 1 like this? Then we can multiply by the reciprocal. All right, this is somewhat getting closer to this, but it's not quite there. But we can manipulate this a little more to make that look a lot closer to that. For example, because the order doesn't matter when we multiply, I can swap this 2x and this cosine here, like this. Ah, this is getting much better. All right, but it's still not quite right, because up here I have x, and here I have x and 2x. Is there something I can do to make these two pieces the same? Well, yes, actually. What we're going to do is we're going to multiply this by 1/2. Let me write that out over here. Because if I take a half of 2, I'll just get 1, or in this case maybe just x. But if I multiply the bottom by 2, I better multiply the top by 2 as well. Or, excuse me, by 1/2. All right. Now remember, the order that we multiply in doesn't matter, so here's what I'm going to do. I'm going to take the 2x and multiply it by 1/2, and I'm going to take the 1 and also multiply it by 1/2. Let's see what we get. Here we go. This is better. All right, we were approaching 0. If you look back at the beginning, this piece, sine x over x, I know is equal to 1, which makes me wonder what to do with this piece here. Well, why don't we just try substitution? I know the first piece is 1, then we've got a 1/2 over the cosine of 0. The cosine of 0 is just 1. 1/2 divided by 1 is still 1/2, and the 1/2 times 1 is equal to 1/2. That's our final answer. All right, let's see if we can find this limit here. We're going to try to find the limit as x approaches -2 from the right. So let's start with substitution. Well, let's see here. In the numerator, we just get 2 with a negative sign. So let me write that out over here. That's just -2. In the denominator, we get -2 squared minus 4. So that's 4 minus 4, which is 0. Think about the previous problems we were working on. We got 0 over 0. That actually meant something special, and this also means something special. If you ever get not 0 divided by 0, that means that you're actually approaching a vertical asymptote. The goal here is to figure out how we're approaching it. As we approach it, is our graph going up? Is it going down? Are they both going up? Let's take a look here. To figure out whether it's going up or down, what we're going to do is we're going to draw a number line. We're going to pick the number that we're approaching, and then we're going to pick another number, which is very close to this one. And because we're approaching -2 from the right, we're going to pick a number that's very close to -2 from the right. In fact, think of it this way. We're going to pick a number that is very, very, very close 3 times, 3 decimal places. That's how close you want to be. If you pick a number that's too far, this method may not work. The closer, the better. All right, we found our number, -1.999. Now we're going to take -1.999 and plug it back into our limit here. -1.999 squared minus 4. And let me put this negative up with the 2 like I did up here, and recognize that the numerator is always going to be negative because of that. Believe it or not, you don't actually need to do the math here. All you need to know is your final answer negative or positive? You'll see why in just a second. Okay, let's take a look here. If this was -2 squared, that would just be 4. But this is -1.999 squared, so it's going to be a teeny tiny bit smaller than 4. And if we have a number that's slightly smaller than 4 and we're subtracting 4 from it, our final answer is going to be a negative answer. Since the top was negative and we're dividing by a negative, that means our final answer is a positive answer. So what does it mean? Well, I'll show you what it means. It means that the limit as x approaches -2 from the right is equal to positive infinity. In other words, if we have a vertical asymptote, let's see here. Let's say our vertical asymptote is over here at -2, and we're approaching -2 from the right, our graph is going straight up like this. So infinity is our answer. Our first at infinity limit problem. Now in the previous problems we were doing a lot of substitution to see what we got, but here we can't really do substitution. How do you substitute negative infinity in for x? You can't really do it. So what you have to do instead is analyze the problem. Take a look here and notice this is actually just a polynomial. What we're going to do is use our knowledge of end behavior to figure out the answer to this. In order to do that, we need to know what the leading coefficient is and the degree. The leading coefficient and the degree are kind of like connected to each other. The degree is going to be the largest exponent, which is 2. The leading coefficient is the number that's in front of our degree here. Now it looks like it's divided by 2, but our leading coefficient is just 1/2, like this, because dividing by 2 is the same as multiplying by 1/2. Now, 2, of course, is even. 1/2 is positive. All polynomials will have the same end behavior depending on their degrees and leading coefficients. Here, an even degree means that both arrows will be pointing in the same direction. Positive means that both the arrows will be pointing up, like this. All right, we've almost got our answer here. X is approaching negative infinity of our polynomial, so what I need to do is go further to the left and see what our graph does. And as we go further to the left, my graph is going up. So, because the graph is always increasing as we move further to the left, our final answer is infinity. Ah, our first exponential type problem. Kind of like with trig functions, there are a bunch of exponential type limits that you also will need to know. So for example, as x approaches infinity of e to the x, the answer to that is just infinity. But if you approach negative infinity of e to the x, that's 0. Similarly, you will also want to know what happens to e to the negative x, like this. Luckily, these answers are just the flip-flop versions of these ones here. So using this, let's see if we can answer this. Okay, we've got a negative in front, so we're going to take a negative there. We've got e to the negative 3x. Well, that's definitely closest to this one, especially since x is approaching negative infinity. So it looks like this part here is approaching infinity, and then we have a negative in the front. So that tells me our final answer is negative infinity. Ah, we have another exponential here. Well, let's remember that as x approaches infinity of e to the negative x, we're getting closer and closer to 0 here. We're going to use this to answer this question. Because we have e to the negative 4x, and that's definitely most similar to this, that means that this piece right here is getting closer and closer to 0. And then we're subtracting 1 from it. In other words, what this means is we're just going to end up with 0 minus 1, or negative 1 is our final answer. Ah, another exponential problem. These ones can be pretty tricky depending on how they set them up. But this is a good one because it utilizes a fact that you will need to know about exponentials. And that is exponentials will always grow faster than power functions like we have up top here. So what that means is as x gets bigger and bigger and bigger, the denominator here is going to be growing faster and faster and faster compared to the numerator. So if you take a number and divide it by a really big number, you're actually going to be really close to 0. And since we're approaching infinity here and we're finding the limit, that means this piece right here is going to 0. And then we're subtracting 2. So what that means is we're going to have 0 minus 2, or just negative 2 is our final answer. All right, so x is approaching infinity, and one of the first things I notice is that we have a square root here, which makes things a little bit more tricky, but not impossible to deal with. Here's what we're going to do. We're going to focus on the largest piece up top and the largest piece on the bottom, like this. And then we're going to try to simplify. 2x will just remain 2x. And the square root of 3, well, 3 is not a perfect square, so we're just going to leave it as the square root of 3. But I can simplify the square root of x squared. You might be tempted to say the answer is x, but that is actually incorrect. The correct answer is absolute value of x. Anytime you take the square root of a number, your answer has to be positive. This is actually really important in these questions. If you don't include that, you could get the wrong answer. All right, now, I notice that we have x to the first over absolute value of x to the first, so their exponents are the same. I can't just cancel them out because of that absolute value, though. So here's what we're going to do. we're going to go back up to this problem and see that we're approaching infinity. So I'm going to pick a positive number and plug it in for x. Let's just say 10. Well, check this out. The absolute value of 10 is 10. 10 divided by 10 is 1, so those will go away, leaving us with just 2 over rad 3. And that actually is our answer. We could rationalize the denominator here, and this one is simple enough that I think we should. So I'm going to multiply the top and bottom by rad 3 over rad 3. My final answer is going to be 2 rad 3 over 3, like that. All right, we've got the limit as x is approaching negative infinity here. I can't do substitution because of the infinity, but this is a rational function over here, which means that I can compare the largest piece in the numerator to the largest piece in the denominator. That would be the x squared in the numerator and the 2x in the denominator here. Don't forget the negative 1 is going to be along for the ride. All right, let's try to simplify this. Let's see here. We're going to get negative x over 2. Or I'm going to write this as negative 1/2 times x. Because once we get to this point, we can use our knowledge of end behavior to help us answer the question. Notice that the leading coefficient is negative 1/2. In other words, a negative number. The degree of what we got here is 1, which is odd. So the end behavior for an odd degree and negative leading coefficient is going to be like this. 1 arrow up, 1 arrow down. All right, now back to our problem. X is approaching negative infinity. So that means as we move further to the left, it looks like our graph is shooting straight up, which means our final answer is just going to be infinity. All right, we're finding the limit as x approaches infinity. This is another rational function. So if I compare the largest piece up top to the largest piece in the bottom, I notice that the degree of the numerator is 1 and the degree of the denominator is also 1. This immediately helps me find the answer. In fact, we're going to take the leading coefficient of the numerator, which is just 1. There's like a hidden 1 right there that we don't write in. And I'm going to divide it by the leading coefficient of the denominator, which is also 1. Don't forget that this negative is going to be along for the ride. Our final answer is negative 1. And what we've actually discovered here is that the horizontal asymptote is negative 1. And as x approaches infinity, this equation here is getting closer and closer and closer to that horizontal asymptote. All right, for this problem, x is approaching infinity of this function here, a rational function. Let's compare the numerator to denominator. The denominator has a degree of 2. Well, there's not even an x in the numerator, so that means the degree of the numerator is 1. In other words, the denominator has a bigger degree. When that happens, that means the denominator is going to be growing faster than the numerator. And when that happens, your answers are going to be getting closer to 0 as x gets bigger. This is always true. If the denominator gets very big, even very big in a negative direction, so even if x was approaching negative infinity, you would still be getting closer and closer to 0. In other words, the horizontal asymptote is y equals 0. And this function is constantly getting closer and closer and closer to 0, whether x is approaching infinity or x is approaching negative infinity. There are a couple of tips and things I want to point out as we go through these problems. My first tip has to do with negative signs. I cannot tell you how many students I've seen make mistakes with negative signs. In one of the problems, actually quite a few of the problems, there was a negative at the very beginning. That can be very easy to miss. And even if you notice it, you may accidentally forget to write it out in your next step, or your next step, or your next step. You have to make sure you bring it along for the ride as you go through all of your steps. If you don't, you'll end up with the wrong answer. So be vigilant for negative signs like this. Speaking of negatives, I can't tell you how many times I've seen a student do something like this. They'll have a fraction like this where they're subtracting, and they'll get 2 minus 2 plus x all over 2 plus x. The 2's will cancel out, leaving them with x over 2 plus x. But believe it or not, this is incorrect here. Can you see what the problem is? You see, when you're subtracting, you have to subtract the entire piece here. But when I was writing this out, I only did minus 2. To do this correctly, you have to think of it like distributing this 2 to all the pieces over here. So you do get 2 minus 2. You also get minus x. And when those 2's cancel out, you're left with just negative x on the top instead of x like this. Always be careful of things like this. Another tip for you is to read the question very carefully. In one of the problems we did this limit as x is approaching 1 from the left. Now, believe it or not, a lot of students will sometimes just look at a problem and start working. They may not notice that there is a little minus sign up here. This is actually going to change how you approach a problem a lot of times. In fact, if you didn't notice that and just started working, you might try to find the limit as x approaches just 1, which is quite a bit more work than just finding the limit as x approaches 1 from the left. Another thing that I've seen students do sometimes is they'll see this minus up here and think that x is approaching negative 1. Of course, that's not what the minus sign means up there. That means from the left. So I guess what I'm trying to say is read the question very carefully before you actually start your work to make sure you know what it is you're approaching and which side you're approaching from. You may need to approach both sides if that's not there at all. Another thing that I've seen students do has to do with their equal signs. Let me show you an example of something that somebody might do. They might look at this limit problem and look at the denominator and think, ooh, that needs to be factored. Well, okay, let's see here. This will factor into x plus 1 and x plus 2. These will cancel here and here. Now, going back here, we're approaching negative 1, so let's plug negative 1 in for x. And then doing the math here, my final answer is negative 1. Now, here's the thing. This is the correct answer, but all of these equal signs don't necessarily follow. For example, I did have a limit right here, but in the next line, it's gone. Where did it go? It can't just disappear like that. I get the train of logic here. You want to work on this and try to factor it first, which is perfectly fine because you can factor it. And in fact, these do cancel, and it is equal to this. But then take a look here as well. Why is this negative 1 over x plus 2 equal to this negative 1 over negative 1 plus 2? There's no real reason for why we're plugging negative 1 in here. Again, I see the logic. You come back here and see you're approaching negative 1 and you plug it in. But the correct thing to do would be to write this limit part out in every step except down here when you actually are substituting negative 1 in. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.